Hi. Today we want to find out, if we can, the value of this nested set of square roots, which will be the square root of x plus the square root of x plus the square root of x plus the square root of x ... forever for x greater than 0. Well, in order to do anything like that, the first thing we have to do is we have to show convergence of the thing. Does this really have a limit? So in order to do that, we have to set up a sequence. And in that regard, we're going to let a sub k equal the square root of x plus the square root of x plus the square root of x ... plus the square root of x, where there are k roots of x on the inside here. K of them. Well, this implies that a k plus 1 will equal the square root of x plus a sub k. We're just adding another x and taking the square root of the rest of it. Well, the weapon we're going to use to show convergence, of course, will be the monotone convergence theorem that we all learn in real analysis. Well, in order to use that theorem, we have to show that the sequence is increasing and the sequence is also bounded above. Okay. Well, we're going to use induction on both those criteria. So first we claim that a sub k is less than a sub k plus 1. In other words, we're going to show our sequence is increasing. Well, our base case, we can say a1, which equals the square root of x. Well, clearly that's less than the square root of x plus the square root of x, which equals a2. So in other words, a1 is less than a2, and that completes our base case. Now, for the inductive hypothesis, we're going to assume that a sub m is less than a sub m plus 1 for some m greater than or equal to 1. Well, adding x to both sides, this implies x plus am is less than x plus am plus 1. Taking square roots, this implies the square root of x plus am is less than the square root of x plus am plus 1. Well, this of course implies that am plus 1 is less than am plus 2. This is just the definition of am plus 1. This is just the definition of am plus 2. And therefore, the first part of our proof is over. We have shown by induction that a sub k is less than a sub k plus 1 for all k greater than or equal to 1. Now, let's go to the boundedness part of our proof. All right, we further claim that a sub k is less than x plus 1 for all k greater than or equal to 1. All right, our base case again is a1, which equals the square root of x. And this is clearly less than x plus 1 for x greater than 0. Now, our inductive hypothesis, we're going to assume that a sub m is less than x plus 1 for some m greater than or equal to 1. Okay, we add x to both sides. This implies x plus am is less than 2x plus 1, which implies am plus 1, which equals the square root of x plus am, must be less than the square root of 2x plus 1, since the square root is an increasing function. Okay, Well, let's let f of x equal x plus 1 minus the square root of 2x plus 1. Well, then f prime of x will equal 1 minus 1 over the square root of 2x plus 1. And we want to find out where f prime is 0. So f prime of x equals 0 will imply that the square root of 2x plus 1 must equal 1. Obviously, this has to be 1 here for this thing to be 0. Well, this implies that x has to be 0. And as x gets bigger, this part gets smaller. So we have 1 minus something that's getting smaller and smaller. So we can say that f prime of x is greater than 0 for x greater than 0. Therefore, f of x is increasing for x greater than 0. And also, of course, f of 0 is simply 0. Okay, well, this implies that the square root of 2x plus 1 then must be less than x plus 1 for x greater than 0. Therefore, a sub m plus 1 is less than the square root of 2x plus 1. We found that right here. And now this is less than x plus 1. So we started with assuming am is less than x plus 1, and we wound up finding that am plus 1 is less than x plus 1. Therefore, we have shown both parts of our proof, where we needed to show increasing sequence and an upper bound of the sequence. So, our sequence of AK is we now know is increasing and bounded above. Therefore, by the MCT, the monotone convergence theorem, our sequence A sub k converges. Well, what does that mean? That means we now can write the limit of A sub k as k approaches infinity. We can let that be equal to some alpha. We couldn't do that until we had shown convergence. And of course, we note right away that alpha has to be greater than 0. So, we can say that the limit as k approaches infinity of a sub k plus 1 must equal the limit as k approaches infinity of the square root of x plus ak. Remember, we found that right off the bat here, taking limits on both ends. Well, we can take that limit on the inside, since the square root is a continuous function. So this equals the square root of x plus the limit as k approaches infinity of a sub k. Well, taking those limits then, this implies that alpha, this will be alpha then, equals the square root of x plus alpha. This will be the square root of x plus alpha then, which implies we square both sides, bringing things together. This says that alpha squared minus alpha minus x equals 0, which implies that alpha equals 1 plus the square root of 1 plus 4x over 2, using the quadratic formula. And noting that, of course, alpha must be greater than 0, so we don't use the negative square root here. I hope you enjoyed this video. It'll give you a test of your real analysis ability and your proof by induction abilities. And if you liked it, please give it a like. Thank you so much.